Hi class, we're here for the next section. We're starting chapter 4. Chapter 4 is all about exponential functions. So in this chapter, we're going to analyze the graphs of exponential functions, how to apply them in different situations. We're going to look at some more limits and things of that nature, right? So we're going to start off chapter 4 with 4.1, which is exponential functions. So the definition of an exponential function that has a base of a, where a is a real positive value, right? It's a positive value, and it cannot be 1, okay? So it's going to be, or 0 in this case, right? So 0 is not considered positive or negative, so that kind of, this condition right here, being a positive real number, excludes 0 already. So the only value that we're not looking at then is a being 1, and we'll talk about why that is. Okay. Here, x is also going to be a real number. It can be any value. There's no restrictions on it. It doesn't have to be positive. It doesn't have to be negative. It can be 0. It can be 1. It can be all kinds of things, right? The form is f of x, right? Our function is a raised to the power of x. So for exponential functions, we have our base of a, and our inputs are in the exponent position, right? We're going to be looking at a lot of the rules. We're going to be using the rules of exponents. So if you are fuzzy on your exponential rules, right, multiplying two exponential terms that have the same base but a different power, or dividing two terms that have the same base but a different power, right, things like that. I suggest you go ahead and review chapter 1. So it was somewhere in chapter 1, 1.2, I believe, that we were talking about these sorts of functions and the rules of exponents. So if you're a little fuzzy on those rules, I suggest you pause the video and go refresh on those. So why do we restrict a in these ways? So let's kind of take a look at those. So here, the possibilities for a are that it is between 0 and 1, or that it's larger than 1. If it's between 0 and 1, then that means basically it's a fractional value, it's a decimal value, something to that nature, right? And our function is going to be decreasing, okay, exponentially. If it is larger than 1, okay, so from 1 to any large number, it's going to be exponentially increasing, right? The reason that we can't allow a to be 1 is because if we have a base of 1 to any power, we're just going to get 1 out again, right? 1 to the 12th power is 1. So if our base is 1, our function is going to equal 1 for any input that we plug in, right? Any value of x that is a real number. If our base is a negative number, then what happens is it is going to alternate back and forth from a positive value to a negative value as we plug in different values of x, right? If this is negative 2, for instance, when this is an even number, I'll get negative 2 times negative 2, for instance, will be positive. If it's an odd number, negative 2 to the 3rd power, for instance, I'll get out a negative value. So it'll bounce back and forth between being positive and being negative, and it will not be a continuous function. So let's just take a quick trip over to Desmos real fast and kind of look at what that would look like as a function. Okay, so now that we're in Desmos, let's say that our function is 2x. So we'll go 2 to the x power here, and as you can see, it is increasing. If it was, let's say, 1/2 x, okay, I'm exponentially decreasing. As I move forward, my function is getting smaller. Okay, so let's say then that we had just 1 to the x. So as you can see, excuse me, you get just a constant function, right? It's just a constant function 1 everywhere. Output is always 1. So let's say we have a decreasing function and we change it to negative. Okay, so the way that this works, okay, is now you can see it's a bunch of dots. Okay, so as I plug in different values of x, I alternate from being positive to being negative, right? Positive, negative, positive, negative, positive, negative. And so the more I zoom in, right? You see Desmos is having a lot of problems trying to graph this function for us. What happened? Oh, that's why it's just signing here. Okay. All right. So if I go negative, yeah, it has a problem trying to do this for us. Right? And so if I put negative here, all that's doing is saying that this whole function is negative, and that's why it just flips over the axes, right? However, when we have it inside here, right, a negative value to the power, you can see now that Desmos, I broke Desmos, right? It's not working anymore. Okay, so we restrict this to being to only being positive and not being 1. Okay, so that's how that works. Okay, so when our function is in this form, right, just a to the x, our y-intercept is always going to be 1, right? Because remember what the y-intercept is? It's what happens when x is equal to 0. So if I plug in 0 here, it's always going to be 1, right? Anything to the 0 power is always 1. So my y-intercept for this type of function is always 1. Now if I had some number in front, like if this was f of x equals 3 times 2 to the x, for instance, then my y-intercept changes, obviously, because now I'm scaling the value vertically, right? I'm amplifying the value. And so then obviously that would change it in the way that we were transforming functions way back in chapter 2, right? So I know we looked at Desmos already, but for our presentation here, I have another graph, right? So when a is larger than 1, our function is exponentially increasing. And when it is in between 0 and 1, not including 0, not including 1, right, open brackets, it is exponentially decreasing. Okay. So again, note that my function is never actually 0. It can get very, very close to 0, depending on, you know, if it's decreasing, it gets very, very close. If it's increasing, it starts very, very small. But there's no way for me to plug anything into x to make this value 0, right? I can't plug in a value here. We take all this out. I can never plug something into this exponential 0 position to make the output 0. It does not happen. Okay, so I can get close to 0, but I can never actually equal 0, right? So note also that if a is larger than 1, right? So that's this increasing function. If I plug in a negative exponent to that, okay, so let's look here, right? So when I plug in negative values, notice that I have small values, right? Also, not only that, but let's say that I write my function as a to the negative x, okay? So we know what that as a transformation does to a function, right? That flips us across the y-axis. So mathematically speaking, a to the negative x is the same as a to the negative 1 to the x power. A to the negative 1 is the same as 1 over a to the x power. This is now in between 0 and 1, right? Because if a is large, let's say a was 3, it turns into 1/3 x if my function is a to the negative x power. Okay, so that will give us a base that's between 0 and 1, and it'll take us from an increasing function to a decreasing function, or as we see here, basically it will rotate it across the y-axis. Okay. Reflection across the y-axis. So let's do an example. Find the equation for the graph of the exponential function in the form of f of x equals a to the x that is provided. Okay, so we have a graph here. We got our x-axis, our y-axis. You can see that this is exponential, and then we're given a point. Okay, it crosses through 0, 1, so we know that it's going to look like this. It's not amplified in any way because the y-intercept is 1, and we're given a point. So to find this actual equation is very straightforward. We just plug in our input and output into the locations provided, right? We just substitute, and then we solve for A. So my 0.481 over 256 will look like this when I plug it into my function, right? I have my output equals A to the fourth. So when I start to solve for A, I basically take the quarter power of each side, right? I take this to the 1/4 power, this to the 1/4 power. But I don't want to leave that as my answer, right? I want to see if I can simplify this at all. So what I can do then, we know that from our rules of exponents, that a fraction to a power is the same as the numerator to this power and the denominator to this power as well. So we'll go ahead and distribute this 1/4 to the numerator and denominator. And 81 I can rewrite as a 4th degree term, and 256 I can rewrite as a 4th degree term as well. So it's 3 to the 4th to the 1/4 power and 4 to the 4th to the 1/4 power. Rules of exponents says I multiply these, which is nice because 4 times 1/4 cancels, and I get a value of 3/4 for my base of A. Therefore, my function is f of x equals 3 to the 4th to the x power. So one of the main applications that we generally talk about when we talk about exponential functions is compound interest. So we've done simple interest before back in chapter 1. So in this section, we're going to talk about compound interest, right? So compound interest is found by the formula A of t is p times 1 plus r over n raised to the power of n times t. Okay. We use t instead of x because we gain interest over time, right? So again, interest is gained when you invest money. Compound simple interest just means that you get a steady amount no matter what. Compound interest means that that amount that you get is added to your value every so often, okay? Every day, every month, every year, what have you. So for our pieces, A of t, right, our function here represents the amount of money that we will make after investing p dollars for t years at a rate of r, right? So r is our percentage rate that we're getting interest, where we are compounding this, right? Either being charged or adding this money to our initial investment at a rate of n times per year. Okay. So the more times we compound in a year, so as n gets very large, the larger the value that we earn becomes, right? So if I invest into something that compounds my interest monthly, I generally will earn more than something that compounds yearly, right? And so this is why your credit cards work the way that they do. Your credit cards generally will compound monthly. So every month, the interest that you're accruing on the credit that you're using gets charged every month. That's why you have monthly bills, right? Okay. Now, we compound, either once up to an infinite number of times, but the value that we're going to earn only increases to a limit, right? So again, if we're talking about investing money, if I am investing in something that compounds very, very often, very large, right? Times per year, number of times per year, I am going to receive more money than if I were to invest in a similar account that compounded less times per year. But the value that I'm earning does not go to infinity in that time period, right? It only increases to a certain limit, right? So the limit of my value of investment as the number of times I compound per year increases does not reach infinity. It reaches a finite value. Okay, so the limit as n goes to infinity, right? So if I plug in very, very large values of n here, very large values of n here, no matter what the p and the r and the t are here, this does not go into infinity. It reaches a stable value, basically. Okay, so let's look at this in an example. So let's say that we invest $2,500 into a money market account that has an average of 0.5% return that is compounded once a year. And so this is actually the average rate right now. Okay, so when I made this problem, I looked at what the average interest rate is for a money market account, and so this is, the standard value at this moment in 2022. So how much money would we have after 5 years? Okay, so I'm investing this much money. After 5 years, I want to know how much money I'm going to have, and I know that the interest rate is 0.5%, and they only give me this money once a year, right? So yearly. So after 5 years, how's that going to happen? So the first thing that we like to do is figure out what our unknown values are, right? What's our P? What's our R? What's our T? What's our N? So my investment amount is $2,500. Okay. My R, remember this is a percentage, so we have to turn into a decimal value because we can't do math with percents. We have to use their decimal equivalent. So this is 0.005. My N is 1 because I compound yearly once a year, right? And the amount of time is 5 years. So when I take all these and I plug them in to my formula, it looks like this. Okay. And obviously we want to simplify this a little bit. So 0.005 divided by 1 is just 0.005. 1 times 5 is just 5. So this simplifies pretty nicely into this pretty basic looking equation, right? So now I would plug this into my calculator and find my value. And since we're talking about money, we want to be accurate to 2 decimal places. Okay. So I get this as my output, 2563.128133, and I cut it off after 2 decimals. Now, we're still going to round, okay? Generally in banks, they don't, right? They apply this whole value towards your account, but they only show you the 0.12, but you do have 8/1000th of a cent also being applied to your account that you wouldn't see here, right? So here we're going to round up. This is basically another cent, okay? So after 5 years, we're going to have $2,563.13. Okay. So let's look at this in terms of compounding more times per year, right? So let's say we compounded monthly instead of yearly. Well, there's 12 months in a year, so that means that they will pay us out, that extra amount of money that we're earning in our interest rate, right, in our account every month. So that means we're going to do this 12 times a year. So our function is 2,500, 1 plus my interest rate over n, which is 12. And then here we have 12 times 5 because, again, this is the total number of times we compound over the time that we're interested in, right? So 12 times a year for 5 years, 12 times 5. Let's find what this is in a decimal value, or simplify it as a fraction is even better, okay? Plug all of this into our calculator to figure out that it's 2563.27445. So it's not a huge difference if we do this 12 times a year instead of once a year, right? It's about, 15 cents more over a 5-year period. So we're not making a ton more. But obviously with large values, there would be a significant difference, okay? So after 5 years, we are making just a little bit more, right? Let's say we compound daily, right? So there's 365 days in a year. So our N in that case would be 365. Everything else stays the same. P is still 2,500. R is still 0.005. And T is still 5. But my N is 365. So calculate all of this stuff, plug it into our calculator to get an accurate value. And we are a little bit larger than we were before. This is 27 cents. This is 28 cents. More like 29 cents, right? So maybe 2 cents more than I had if I did it 12 times a year. And it's what, about 16 cents more than if I do it once a year. Okay, so after 5 years, we would have this amount. So again, as the number of times we compound our interest into our account, the amount that we receive over time increases as well, right? So if n is 1, we have 2563.13. N equals 12. I had a little bit more. When n was 365, I had a little bit more than that as well. Okay, and that is how our compound interest works.